Good morning, everyone. Today, I'm here to present the architecture and a pipeline for data extraction and exposure implemented as autonomous web crawler using Java and Spring Boot. The objective of this project is to demonstrate the ability to build a system that navigates a website, extracts structured information persisted in a database, and then exposes it through a RESTful API. This is a demonstration of a complete data lifecycle from data collection to consumption. Alright, let's look at the central component of this project, which is the crawler service. This is where the extraction logic for the database, or rather, the data, is defined and executed. Let's analyze its design and functionality. In the class, I implement the command line runner interface. This is a deliberate design decision. It means that as soon as the Spring Boot application starts, the run method is executed automatically. This turns the application into a batch process, meaning in the startup, perform its scrapping task, and once finished, it can continue running to serve the data through the API. On each run, it first cleans the database with the delete all method to ensure that the data is always up to date. Let's continue with the scrapping logic using GSOAP. So for the interaction with the website, I have used GSOAP, which is a robust Java library that allowed me to parse HTML. So the crawler is designed to iterate over a predefined number of pages. In this case, I decide on 3 from an ebook e-commerce site. This site is called Books to Scrape. Then inside the loop, as we can see in this line, an HTTP connection is established. The HTML is downloaded and is parsed into a document object. After that, in the data extraction, this is done with CSS selectors, a precise and efficient technique. For example, here it selects each product block on the page and from there some more specific selector. This demonstrates the ability to analyze the DOM structure of a website for target data extraction. And finally, which is important, the process is wrapped in a try-catch block. This allowed me to handle network of parsing errors more robustly to ensure that a failure on a page doesn't stop the entire scrapping process. Let's continue with the data model and the persistent layer. Here we have the book entity and the book repository. So once the data is extracted, it must be modeled and stored reliable. Let's start with the book entity, where I define a simple JPA entity to represent all the extracted data. We have the title field and the price field. I also place a database level constraint with a varchar 500 specific on this column, and now I also use Lombok to reduce code and thus keep the entity cleaner and more readable. We continue with the book repository, which just like in more complex architecture, I always use Spring Data JPA. The book repository extends JPA repository and gives us access to all the necessary database operation without writing a single line of SQL. Now it's important to highlight that instead of saving each book individually inside the scrapping loop, I collect them all in an array list. And then I call book repository points save all, where I pass all the books, and only do this once at the end. This performance optimization is significant, and as it reduces the number of database transactions from many to a single one, drastically improving efficiency. Well, the last step of our pipeline is to make all the collect data useful for other application or service. And I do this through a REST endpoint. So if we go to the book controller, it has a very specific and limited responsibility. It exposes a single endpoint with the get method and the root API books. The controller directly injects the book repository to get all the books. And it's important to note that in this case, an intermediate service layer is not necessary, as there is no complex business logic and the operation is a simple data read. This demonstrates architectural judgment, which is not over-engineered when it's not needed. Now, when the method is applied, it returns a response entity, which gives me full control over the HTTP response, including the status code. Perfect. With application architecture completely broken down from persistent to the controller, the next logical step is to take it to a real environment. A project of this nature isn't truly complete if it only works on our local machine. That's why, from its inception, this API was designed with the mindset of being launched into production, following deployment best practice. So, to demonstrate the complete life cycle, I have deployed the application using a modern and decoupled cloud architecture. The web crawler service runs in containers within Render, while the Postgres SQL database is managed by Neon. Now we are going to validate that this entire ecosystem is working correctly by performing some live text via Postman against the public endpoint that Render provides us. In conclusion, this web crawler project is a practical demonstration of an end-to-end data pipeline. It demonstrates competence in extracting data from external sources with GSOP, efficient data modeling, and persistent with Spring Data JPA, and exposing that the data through a RESTful API. Furthermore, it highlights best practice in building and deploying applications with Docker and flexible configuration. Thank you for your attention. The complete source code is available for your review at the links provided.